Hello and welcome to GradCast, the official radio show and podcast of the Society of Graduate Students here at Western University. I am your host tonight, Gavin Tolometti, and I'm joined with
Reese Paterson.
And today we are joined with PhD student Leah Sacks from the Earth Science Department. How are you doing tonight?
I'm doing well. How about you?
I'm doing pretty good. How about you, Reese?
I'm doing just peachy.
So everyone's been enjoying the cold weather then?
Oh, yeah.
Of course. Yes. As we are recording this podcast, it is minus 21 outside. Nice brisk 21 degrees.
Yeah.
Lovely.
Yeah, I currently have a freezer that's over capacity and I'm leaving stuff outside to stay frozen as I make space.
Yes, nature's freezer, of course.
There is one advantage to living in Canada in the winter, and that is your outdoors is your freezer. So Leah, I think we can jump right into the show. Why don't you quickly tell the audience what is your research that you do at Western?
Well, I just finished doing some research for my master's degree that's on an impact crater on Mars. And I was studying the ejecta, which is all of the material that comes out of the crater. And now I'll be starting to work on some structural geology and looking at fractures on the surface of moons in the outer solar system.
What was the name of the crater on Mars that you focused on, since it was just one?
Hargreaves Crater. And it's sort of near where the rover is going to land in a couple of weeks, I guess, for Mars 2020.
Oh, cool. So it's very close to because they're landing in the Jezero crater, if I'm not mistaken.
Yes. And it's just northwest of Jezero.
Okay, that's pretty cool.
We should preface this episode with the fact that there are 3 geology majors on this episode, both of whom are in the Earth and planetary science degree field, correct?
Mm-hmm.
I'm the odd person out. I don't study space.
But you still study rocks.
I still study rocks, and that's what matters the most.
And it's also a good bonus that this episode will probably be coming out just after the landing, so we'll be hopefully get to see what that's like.
So obviously these craters are important. Is there any type of like Earth equivalent or analog or something that we could see, or is there too much going on Earth that's like too much happening geologically? There's so much stuff going on and it's just too much of a mess.
It is definitely sort of an issue. There's a lot going on Earth. A lot of craters actually are covered up or have been sort of worn away due to erosion. So there's only a handful of craters that actually have real ejecta. So there are a number of craters that the hole in the ground is there, but there isn't a lot of the material that came out of the crater. But there are a couple, and interestingly, we actually think, especially following my research, that the craters on Earth have a lot more in common with the craters on Mars in some capacities than the moon craters do with either of the other two. So Mars has a lot of volatiles and other important components to its crust that the moon doesn't really have in the same way, and Earth does. So Earth and Mars are similar, both in their makeup, and they both have erosion. So there are active processes on both. So in some ways, comparing Martian craters to Earth craters actually makes a lot of sense, even though we do still learn a lot from studying lunar craters as well.
And I guess when it comes to comparing the Mars craters to Earth craters, do you still find the disadvantage of, since the erosion on Earth is such more aggressive and dynamic, that it's hard to find a perfect analog to Martian craters, since everything's either completely covered in vegetation, destroyed by plate tectonics, or covered by sediments, that it's tricky to maybe find that perfect site on Earth to compare to the Hargreaves crater?
Yeah, no, that's definitely true. Part of my research actually did take a look at the Reese Crater in Germany.
Hey.
Yeah. That crater as an analog, partially to help us understand what we were seeing on the surface of Mars, and really trying to connect the orbital observations that I can make, because mine are all done from satellite images, to the in situ field work that you can do on Earth to actually look at the layering in an ejecta blanket and the internal structure. So there are very few options for analogs on Earth, but we do see them, and my research actually did work to sort of connect the Reese Crater to Hargreaves Crater and note some of the similarities that we see between the two of them. They both have this layered structure where you can see multiple, like at least 2 periods of emplacement where the layers of the ejecta were put into place. So it's difficult, but still important to connect them. But in that way, now we can use the information that we can learn from craters, Hargreaves type craters in particular, on Mars to help us understand some of what may have been in the past around certain craters on Earth. So it sort of goes a little bit both ways when we can connect the analog on Earth to the crater that we see on Mars.
And for Hargreaves, you said you used spacecraft data to look at the ejector for that crater. And for the Reese crater, did you get a chance to go in the field and get to see what this ejector looks like? Or did you have to look at samples that were maybe brought back from past field deployments?
Yeah, no, I didn't get to go in the field, unfortunately. I wish. But other members of our research group have gone to the Reese and have written up some information about their observations there. And there are some hand samples as well. So I did a lot of sort of going over what they had found and then trying to use that as an example of this sort of layering on Earth. So it was a lot more about just connecting what we already know about on Earth to the new data that I was adding from Mars.
I feel as if I should switch my thesis and go and study the crater. It'd be fun.
Yeah, I feel like for you, Reese, it'd be like the perfect match.
Yes, exactly. Yes. So you mentioned the rover that was going to be landing, or like in the very, very beginning. So are you excited? Are you going to be getting data for your thesis from that rover, or is that going to be included? Or
so I've finished that degree technically. So I'm not actively working on that that project anymore. Well, not really actively working on that project anymore. So I won't be getting any new data that would be part of my thesis or anything. I have submitted that thesis, but I and completed it. I defended it. It's done. But
yay.
A lot of the information that I learned doing my thesis is applicable to some of the study site that they'll be looking at. So data coming from the rover will be familiar and perhaps applicable to sort of make a further understanding of both what I already learned and, you know, perhaps my research will influence some of what they learn at Jezero, although it'll be a while because they're sort of in a different area at the beginning. It would be once they get out of the crater that it would be more relevant. But yeah, we'll see. It should be pretty exciting. I'm looking forward to the landing so we can see that area of Mars. It's exciting that that area that I'm so familiar with will be part of upcoming data coming from Mars.
Do you want to quickly describe to the audience what is it about this area on Mars that's made it so appealing for NASA to send a new rover? Because we've had Spirit, we've had Opportunity, and Curiosity is still roving around. But what is it about Jezero Crater that made them want to send a new rover?
Yeah, for sure. So there's a couple things. First, the part that's most relevant to what I've been doing is that the bedrock area around the crater is some of the oldest crust on the surface of Mars, to our knowledge. So it's Noachian bedrock. Noachian is the time period on Mars. So it's particularly old, which really would help with our understanding of how Mars has changed and sort of how its initial crust formed. A lot of other sort of evolutionary things regarding Mars. But the more immediate parts of what they're looking at Jezero is that it's the site of a delta, a river delta. So there's a river that empties out into the inside of the crater. So there should be river sediments. They think that there was once some evidence of a lake in Jezero Crater from that river. So we're going to see probably a lot of interesting sediment that will give us clues about how much water was once on the surface of Mars, how long that period existed. Were there multiple periods where there was water on the surface of Mars? So the water aspect and the possibility that there may have been life or components of life in that area is partially why it's so interesting. We've done a lot of looking for water on Mars in the past, and part of Mars 2020 Perseverance, the goal is to actually look for signs of life and the materials that we need to make up life. So could there have been life in the past? Could there be life in the future? That sort of thing. They're going to be doing some sampling. It's part of the point of the Mars 2020 rover is to take samples and collect them. And then a later mission will come back and pick up those samples and return them to Earth. So sample return from Mars is a big goal of these upcoming missions. And then the final component, there's a part of the interior of the crater has a chemical signature that some attribute to a volcanic origin or some igneous rock origin. So those they're mafic signatures, I suppose. Those signatures are also attractive. They want to get evidence or collect samples and see evidence of deposits on the surface of Mars. So the question of whether or not they're volcanic will be presumably answered by the landing in Jezero Crater.
And you said that material that's probably more associated with the crater you were studying is going to be closer to near the end of the rover's journey when they get outside of Jezero Crater.
Yes.
Because you mapped some of this material out, and then so you saw some of this material was quite close to the edge of Jezero.
Yeah, so I did look. I did map out where the edge of the ejecta from Hargreaves Crater is, and it doesn't quite reach over to Jezero, but I looked at the, I had to look at the surrounding material as well as the ejecta coming from Hargreaves, and we actually think that the Hargreaves ejecta may have pulled from that Noachian bedrock to then sort of throw it out onto the surface. So once the rover has sort of done its initial part of the mission inside the crater, the plan right now is to go up the channel, the river channel, and out of the crater into the Syrtis lava areas. But that area also is this Noachian bedrock sort of underneath the lavas. But so depending on what you're looking at, you'd be seeing lavas or bedrock or some of the other components in between those two stages. But a lot of what I've been looking at, the Noachian bedrock, and then also the ejecta from Jezero Crater itself would probably be interesting for me to look at, similar rock layers that we'd be looking at. And all of that will be available outside the crater. So once the rover has been able to make its way all the way out there.
I can't wrap my head around it. It's completely crazy to listen to you talk about this Martian body that's God knows how many kilometers away from Earth, and you could just think of all the geologic possibilities that are out there. And I'm thinking from a sedimentological perspective, and the rivers piqued my interest. It would be so interesting to bring a core back, or even just like a foot or two, just to see what it would be like. But that's definitely in the distant future, not until we can go and return.
One of my most interesting memories when I first got into planetary science was actually the first time that I was able to see cross-bedding on Mars. So they have images from the Curiosity rover where you can really see good cross-bedding in sandstone, and I was like, wow, that's geology on the surface of Mars. It's just true sedimentology that we're doing here.
For the listeners out there, this is one of the most basic things that every single geologist learns, regardless if you're in a hard rock or a soft rock geology program, if you're obviously if you're learning in space or if you're learning on Earth, it's all the same. So that's fun. That's interesting.
Yeah, I remember from my undergrad, they said, like, look out for cross bedding, and then you'll know there was flowing water.
There's actually a joke in the Martian community, although I wouldn't consider myself fully in part of that necessarily, but about how the geologists and planetary scientists keep rediscovering water on Mars. Like there's more and more evidence that there once was water on Mars. And so everything that they do further proves that in some capacity there once was water on Mars.
Yeah, it must come up a lot that where people constantly ask if there's actually still liquid water on Mars, because we still have no idea if there is, but as the big consensus on the surface, there definitely isn't any liquid water. But we do, like the River Delta and Jezero Crater is a good example showing that there once was flowing water on Mars. It was just millions, if not billions of years ago, when it was able to be stable on the surface at least.
There's some debate a little bit about some of those channels and whether or not they may have been glacial or glacially related rather than sort of fluvial or rivers, the way that we conceptually think about them, which is an interesting just sort of side note to think about, is that not all of them, but some of them may have been influenced by water from glaciers as opposed to, and under glaciers as opposed to just rivers, which is interesting.
I guess it opens the door to more analog work you could do on Earth, because since we have so many glaciers, we can be able to find almost as many analogous or similar geological features to compare to Martian ones.
Yeah, I think so. I imagine people who study glaciers a lot probably took some interest in that paper and are interested to see whether or not they can do some sort of study on Earth that might give a better understanding of the feasibility of that as a mechanism for creating those channels that we see.
Glacial geologists and their ice cores and all of that fun stuff. Is there any, like, again, from a sediment perspective, like you're talking about cross bedding and various other structures that I won't go into because I'll just continue on forever and ever. But I guess one of the features is that when there's no water, there's something called desiccation cracks, where you kind of have these like polygon shapes that get filled with sediment, and they're very distinctive. You can tell that there's definitely been like a dry spell. Is there anything that would, I guess, like be indicative of ice or water that's not bedding or anything? Like, does ice crack the sediment? Like, what does it do?
Yeah, I imagine, as you know, someone who's a glaciologist or a permafrost specialist would definitely have a real answer for you. But I do know there's a lot of there are many polygonal features on the surface of Mars. There's a lot of evidence of various processes forming polygonal shapes. So there's another grad student within the department who's working specifically on permafrost features in mid latitudes on Mars. So there's definitely evidence of paraglacial in the sense of permafrost and similar features, as well as some evidence of glacial processes on Mars as well. So there's a lot of evidence of certain things, and we have seen actual ice. I think it's the Phoenix lander dug a hole with its foot in the snow, and there was ice that was revealed. But we see ice actually with some craters. Some craters impact and they reveal ice in latitudes that are not just the poles. So there's ice at the poles of Mars, but we do see it under the surface, where we know that it's not exposed, but there's ice underneath. So people are working to connect surface morphology with evidence of ice, so that we can get a better idea of how much ice is actually near surface on Mars, not just at the poles.
Yeah, and for everyone in the audience listening, if you are interested to learn, as Leah said, more about ice and the surface features that could be associated with ice, you should check out episode 269 with PhD candidate Shannon Hibbert, where that's the person Leah was referencing. So I definitely go check out her episode to get a more bigger perspective of what ice on Mars and the processes associated with it are actually like and what's being studied. But speaking of ice, because your master's work you looked on Hargrave and the ejector material, but in your PhD, I know you only just started, so you're probably still trying to figure everything out. But you're now transitioning from Mars to Icy Moons. Do you want to tell us a little bit about what brought you to Icy Moons?
Yes, or I would love to. I don't actually, I'm not sure that I have a really good reason that I like the Icy Moons, but I actually, before I did my master's, I had interest in working on Icy Moons. I think part of it is that I'm very fascinated by Europa and Enceladus and the possibilities of sort of an ocean that is covered over with a crust of ice, and that existing out in the outer solar system, I think is fascinating to me. And that, there are cracks in the surface of Enceladus that have jets, with molecules in those jets that, eventually we may determine that there might be life down under the surface of one of those planets. And that's incredible. And the possibility of that is like amazing to think about. So my upcoming work that I haven't started yet, well, I've started, but not research, but we'll be looking at fractures on a couple of other icy moons. So I'll be looking at, some slightly undecided, but I'll be looking at a couple of smaller moons to look at fractures, and try to understand a little bit more about how those fractures form, what sorts of things play into the formation of those kinds of fractures. And hopefully the idea would be that studying fractures on these smaller bodies and on other places would help us better understand those icy moons and planets that we see that have very large fractures and access to water beneath them. So understanding those fractures is important for us to continue learning about and understanding the water and the possibility of life that we see on some of these moons in the full outer solar system.
All right. Wow. I still can't wrap my head around it. I'm still processing the fact that all this sediment and all that fun stuff. Like, obviously you're aware of it, but like I'm literally out in space. I'm literally out in space trying to understand it. So real quick, you mentioned 2 celestial bodies. Where are those celestial bodies in the solar system?
So Europa and Enceladus are both moons of Jupiter.
No, I think Europa is, but
Enceladus is a moon of Saturn, maybe.
Enceladus is Saturn.
I think that's true. As soon as I said that, I was like, no, one of them.
It's okay. I made a similar mistake earlier, and I thought, oh dear.
Yeah, no, Europa. I know Europa is the moon of Jupiter, and yes, Enceladus, I believe, is Saturn. So, yes, they're both very large moons, distinguishable in the night sky. Well, with certain telescopes, but of the large gas giants.
All right. Okay. Now I've got a geographical perspective. Is that even right?
Yes.
You could say cosmological perspective.
Yeah.
I don't know if that's the right term either. But no, I think with Europa, like in terms of planetary science missions, we have the Europa Clipper mission that's going to be it's going to be a while before it's even launched, but it was announced that it will be happening, which is very exciting because it will be the one of 2 icy moon missions that will be happening in the next definitely couple decades or so.
Yes, Europa Clipper should be pretty great. I believe I don't actually I'm not as in the know about what Europa Clipper entails, but from what I know, it's going to be an orbiter. So it will stay around, well, by orbiter, I mean, it will not land on the surface in this sense. So it will be doing atmosphere analyses and imaging the surface, doing a lot of spectral work, so trying to understand the compositions of what they're seeing. And I think doing some like altimetry, trying to get some idea of topography and elevation. I'm trying to think about what else. There's a lot to learn about Europa. A lot of things that we don't understand about Europa. Europa seems to have a lot of surfacing processes, so it doesn't have very much in the way of crater evidence on it. And craters are one of the ways that we both age date planetary surfaces, but also get an idea of how active their surfaces are. And because Europa has very few craters on it, we get the impression that there's something that is actively recovering the surface of Europa. So understanding those mechanisms, there's a lot of theories about what's going on. I have not looked into them specifically, so I can't really give you a full overview, but understanding that and trying to understand how much access we have just being on the surface of Europa to the lower layers of Europa, how much of the sort of lower subsurface material is making its way to the surface as part of that resurfacing process. So understanding that is one of the big questions going to Europa. Again, sort of leading toward this possibility of, are the components for life available below the surface of Europa, on the surface of Europa? Is there life in the solar system beyond us? Is really, that's the age-old question of planetary science, really.
Oh, that's going to be a lot to take in for everyone who's just being delved into the world of Icy Moons. And I think we're definitely going to, when this episode comes out, show you guys images of Europa and Enceladus so you can get an idea of what Leah's talking about here, because they're very cool Icy Moons to look at. And unfortunately, we are just about to get to the end of our show, but Leah, is there any way people can contact you to learn more about your work and learn more about Icy Moon research?
Of course. So you can follow me on Twitter at, my Twitter handle is @LithicLeah. And then my website, which has a blog, which I occasionally will post research updates on, is leahinspace.com. You're welcome to find me on either of those or on LinkedIn if you want.
Sounds good. We'll leave links in the show notes for everyone. Thank you again for coming on, Leah.
Of course. Thanks for having me.
So this has been Gradcast, the official radio show and podcast of the Society of Graduate Students here at Western University. I've been your host, Gavin Tolometti, with co-host Reese Paterson. We have been speaking with Leah Sacks, who's studying planetary science in the Department for Earth Sciences. If you would like to learn more about the show or come on as a guest or maybe join the committee, you can email us at gradcastradio@gmail.com. We are on Radio Western 94.9 FM. You can follow us on Twitter and Instagram at Gradcast Radio, or you can download our episodes on podcast apps such as Podbean, iTunes, and Spotify. And alternatively, you can find our episodes on our website at gradcast.ca or on our YouTube channel at Gradcast Radio. Thank you for listening and have a great night.